Let's have a review of what you already know from our past lectures. So to increase the precision, accuracy, and features of modern instruments, we always rely on physical parameters in which their response to the environment can be predicted based on the equations or past experimental data. And to get rid of human error, we build electric circuits that will do the measuring or at least the mapping of physical response into consistent electrical signals, and these signals are translated into human-readable form. So instruments in which the quantity to be measured varies the magnitude of electrical signals supplied by an external power source are called active instruments. When designing active instruments, we must be able to keep track of various electrical quantities like voltage, current, or resistance, and check if these physical quantities in different parts of the circuit are consistent with your desired output. Now, these three quantities, assuming they are measured at constant temperature, are related by Ohm's law. So this is Ohm's law, V equals IR. The importance of knowing the physics behind the basic design of instruments that measures these quantities are the following. First, the user can design his or her own multimeter or other instrument with related function. Second, it allows the user to carefully handle a multimeter without looking at a manual. Third, the user can test a circuit or a device by the proper application of multimeter. And lastly, the user can test or debug its own multimeter before measuring the properties of an external circuit. Current is the amount of charge that passes through a given point per unit time. The design of most electrical devices rely on a current flowing in one direction, and I'm talking about DC or direct current circuits. You are already familiar with the basic ammeter and voltmeter design that measures current and voltage in DC circuits. However, when your input involves alternating current, so for example, the y-axis represents the voltage amplitude of the signal and the x-axis represents the time. So when you have a voltage signal coming from an alternating current, it looks like this. However, when your input involves alternating current, it is easier to measure the voltage if you truncate the part of the current that flows in the reverse direction. In other words, we just use the positive valued voltage and assume that through these values, we can represent the overall voltage of an AC signal by calculating, for example, the peak voltage or the root mean squared voltage, etc. In another design called the AC full wave rectifier circuit, we include the contribution of the negative valued portion of the AC signal and calculate certain quantities like VRMS or peak voltage to represent the signal coming from the AC circuit. Also, we introduce another way of measuring potential difference by creating a null-type instrument. Technically, voltage and potential difference are the same. Here, we vary the resistance of the measuring instrument by adjusting the sliding contact. If you forgot the concept of null-type instrument, please watch my lecture about this. The link is in the description box below. When it comes to measuring resistance, we could just simply use an ammeter and voltmeter to measure current and voltage, and then use Ohm's law to calculate for the resistance. But as I pointed out from previous lectures, the shunt resistor of the ammeter and the multiplier resistor of the voltmeter can affect the reading of the current and the voltage, and this error could cascade in your calculations. And this is where we introduce a bridge circuit with variable resistor to measure the resistance of an unknown component or device. However, these instruments try to represent the voltage, current, and resistance with a single value whether our input comes from a DC circuit or an AC circuit. Apparently, these are sufficient if we have an input voltage or input current that do not fluctuate over time. But when we want to capture how electrical signals fluctuate over time, these instruments are not enough. Hence, we explore another instrument called an oscilloscope. An oscilloscope is a device that displays the time evolution of calibrated voltage amplitude. It is used for analyzing, designing, or repairing circuits in which electric signals changes with time. There are components or devices that converts changes in physical quantities into electrical signals called transducers. We will discuss transducers in later chapters. Through the use of these transducers, oscilloscopes can literally display a graph of the changes in any physical quantity because of its ability to convert other forms of energy into electrical signal. So let's view some oscilloscope. If we look at any oscilloscope, its interface must have a screen where we can view the voltage versus time graph of the input signal, the ports where we are going to feed the signal, and some knobs to change various settings like the time scale or time per division scale and the voltage scale. Here, notice that we can vary the voltage per division settings of each input. Here we have input 1 and input 2, therefore we can also simultaneously vary their scales using this voltage per division knob and this second voltage per division knob. If your oscilloscope has two channels, then two different voltages may be displayed simultaneously for direct comparison. So oscilloscopes can basically measure the frequency of oscillating signals, circuit noise levels, period and voltage values of signal waveforms, phase shift of one signal relative to another signal. We can also check whether an interference disrupts a signal. And finally, through oscilloscopes, we can determine how much signal is AC and how much signal is DC. We will discuss its basic controls later, but for now, let's peek inside an oscilloscope. So here we have this electron gun assembly that emits electron and focuses it into a beam. So essentially, it can be a hot filament object and so on that releases electrons, and then through electromagnetic field, they try to accelerate such electron in such a way it becomes an electron beam. And it passes through these horizontal deflection plates and through these vertical deflection plates until it reaches the screen. We can actually picture this screen as having a y-axis that corresponds to the voltage level of the input signal and the time axis. Through the time axis, we can discern whether the voltage is time dependent or not. And the z-axis, which is not apparent here, but the z-axis actually refers to the intensity. So if you will be operating an actual oscilloscope, you can adjust the intensity of the electron beam in such a way you can view a very thick line representing the voltage signal, or you can adjust it to make the plot or graph sharper. So again, the electron beam is passed through this horizontal and vertical deflection plates, then lands on the fluorescent screen. The fluorescent screen usually has a phosphor crystal that gets excited and releases light energy when bombarded by an electron beam. So what you will see in an actual oscilloscope is a glowing screen, but if you try to adjust the intensity, then you'll be able to see a very fine line of plot of the voltage versus time graph of the input signal. The electron beam sweeps from left to right, and once it reaches for example, it begins at the left edge and then keeps on releasing electrons from left to right. So the electron beam sweeps from left to right. Once it reaches the right edge, it is turned off and returned back to the left edge. This switching happens so fast that we can observe a steady line or a steady curve depending on the frequency of the input signal. So again, in this screen, the y-axis by default refers to the voltage level of the input signal, while the x-axis refers to time. The z-axis refers to the intensity, and there should be a knob on the oscilloscope to adjust the fineness of the graph you are seeing on the screen. Also, there should be another knob. So here, this is the brightness knob. Well, it depends on the oscilloscope, but there should be another knob to reposition the zero level of the voltage of the graph. Later, it will become apparent what this zero level means. So I'm not going to discuss the circuitry of a basic oscilloscope because it's beyond the scope of our discussion. My goal here is just to give you an overview. My goal here is to provide you the basic mechanism on how oscilloscope display the input signal on the screen, and of course digital oscilloscopes have an analog to digital converter circuit that allows it to reprint the waveform with the use of a liquid crystal display or LCD instead of a cathode ray. So just to give you an overview, if this is the part where we feed the signal, it is connected to a circuit that regulates the amount of horizontal and vertical deflection of the electron beam, and thus its overall effect is to display whether you have a time varying voltage or simply a DC input voltage. In order for us to examine the different properties of the waveform being fed into our oscilloscope, we must adjust the volts per division scale and time per division scale settings so that our waves will look like this instead of this. So you usually see a waveform that's beyond the volt per division scale. It looks like this. So it's really hard to calculate, for example, the peak-to-peak voltage of the signal. So sometimes when we have a very large voltage amplitude in such a way the waveform doesn't fit into our display even if we adjust the settings, we would like to attenuate the signal. This is where the times 10 attenuation cables comes in. So let's look at the oscilloscope probes. So here are some examples. So if we look at the oscilloscope probes, the one that is being connected on the ports, there is this button for times 1 or times 10 attenuation. Apparently, this button is for enabling attenuation. So for example, when you activate this times 10 button, you're reducing the voltage by a factor of 10. So mathematically speaking, you are dividing the signal so that it would fit into our display. So for example, we have this voltage signal and we read this peak as 10 volts, but the X10 probe is enabled. This means that the actual amplitude of the voltage is 100 volts because we need to multiply this with 10. So when we view the screen of oscilloscope, the x-axis refers to time and the y-axis refers to the voltage amplitude of the signal. Along the vertical axis, this is what we consider one division. And not this one. Similarly, when it comes to horizontal reading, this is what one division looks like. This is what we call the one division for the horizontal reading. So again, the vertical axis refers to the voltage amplitude of the input signal, and the scale is set in volts per division. So again, this is what one division looks like, this line here. This is one division, this is another division, and so on. Similarly, when it comes to the horizontal axis, recall that horizontal axis refers to time. Along the horizontal axis, the scale is set to seconds per division. To give you a demonstration on how to read different values from an oscilloscope screen, suppose this line represents the signal coming from our input, and when we read the signal, the current settings of the oscilloscope are the following. The volts per division is set to 2 volts per div, the time division is set to 1 millisecond per div, and the times 10 probe is off. This button is off, so we don't need to multiply our final output with 10. We are asked to find the DC voltage level, the period, and the frequency. From the zero level of the vertical axis, we count the number of divisions. So 1, 2. So this signal is 2 divisions above from the zero level of the vertical axis. Therefore, the DC voltage level is 2 times 2 division equals positive 4 volts because it's 2 divisions above the zero level. Now, when it comes to period and frequency, apparently, this only applies when we have a sinusoidal signal or a signal coming from an AC circuit. So, therefore, we will not be able to calculate for a particular period or frequency for this signal. So, we will just indicate not applicable. Let's look at another example. So this time, we have an AC signal. After adjusting the settings, we were able to see this kind of signal from our input. So we have these settings. The volts per division is equal to 5 volts per division. Time per division is equal to 2 milliseconds per division. And the times 10 probe is off. So we don't have to multiply our final reading with 10. We are asked to find for V sub PP. This variable means peak to peak voltage, and we are asked to find the period and frequency. It is more efficient to calculate for V sub PP rather than the peak voltage because when you calculate peak voltage, for example this one, you are assuming that this is the zero level of the wave. However, when you encounter a waveform for some unknown reason that the waveform starts at this point and this point, so when you have this kind of waveform, if you want to calculate for the peak voltage, you have to locate first for the zero level of this waveform and then calculate for the peak voltage. However, if you calculate for the peak-to-peak voltage, meaning to say if you start with the crest, begin counting at the crest until you reach the trough, then if you want to calculate peak voltage, you just have to divide this by 2. Again, it is more efficient to calculate for the peak-to-peak voltage first if you want to calculate the peak voltage, because when you directly calculate for the peak voltage, you are assuming that the waveform is perfectly symmetrical with respect to the zero level of the vertical axis. So again, we will just calculate for the peak-to-peak voltage. Essentially, this is the peak-to-peak voltage. So this is 1 division, 2, 3, 4. So 4 divisions times 5. Then the peak-to-peak voltage is equal to 20 volts. Next, for the period, I could just start at the origin and then this is one complete wave cycle. This is the length I'm looking for. The horizontal axis refers to time. Then I'll just count the number of divisions of this length and then multiply it with the time per division. So here I have 1, 2, 3, 4, 5. So the length of this path is 5. So I'll just multiply it with 2 milliseconds to get the period, because 1 period is the time it takes for a wave to complete one wave cycle. So 5 times 2 milliseconds, I'll end up with 0.01 second. Finally, frequency is just the reciprocal of period. So frequency is equal to 100 hertz. So again, when it comes to reading the voltage level or the amplitude of a sinusoidal waveform in an oscilloscope, it is more convenient to calculate for the peak-to-peak voltage, because once you have this information, you can easily calculate for the peak voltage just by dividing the V sub PP by 2. It's now time to practice. For your short quiz, rewrite this table and insert your answers in the blank fields and so on. And this quiz may be handwritten or you may use a word processing software. Now write NA, for example, in this field if some fields are not applicable for certain figures or certain setups. So to start, item 1, item 2, item 3, item 4, Item 5, Item 6, Item 7, Item 8, Item 9, Item 10. When it comes to analysis of two signals that are time-dependent, we have this concept of Lissajous curve or Lissajous figure that facilitates comparison of signal properties just by visual inspection. So before we proceed, recall that parametric equations are a group of functions of one or more independent variables called parameters. For example, I have y that is a function of time and also x that is a function of time. So this bunch of equations are called parametric equations and they have similar parameter, and in our case it is the variable t. So again, for example, we have alpha and it's a function of x, y squared, and z cubed, and we also have beta and it's also a function of x, y squared, and z cubed. Then this group of equation or these equations are called parametric equations and they share similar parameters. In this case, it's x, y squared, and z cubed. Now, there are many applications of parametric equations because it is helpful in efficiently solving other mathematical problems, especially when you want to dissect or segregate some variation of variables. For example, you have y equals x squared. Usually, this is helpful in differentiation or integration. And if we have this relationship and we also know that x equals time, then we can momentarily decouple y and x by writing y equals t squared. So similarly, if we try to use oscilloscope to read two signals, both signals are dependent on time and this is the common parameter between the two signals. So for example, my first signal represented by v sub 1 has an amplitude of A. It behaves like a sine function. And obviously, it's time dependent. And it has a frequency of, let's say, A. And the second signal has an amplitude of capital B. And it behaves like a sine function. So it's also a function of time. And it has a frequency of small b. Now, here's the thing. Remember that our oscilloscope can display the voltage in the vertical axis and the time along the horizontal axis. Let's assume that V sub 1 is displayed in the oscilloscope like this, and V sub 2 is displayed in the oscilloscope like this, as it almost overlaps with V sub 1. What if signal 1 advances by a phase of V with respect to signal 2? Somehow it advances like this. So that's one way of visualizing or comparing two voltage signal on an oscilloscope. Or you could actually separate them by just adding a DC level to one of them. So you could actually picture them as if this is V sub 1 and this is V sub 2. Something like that. But when we position one of the signals along the x-axis and the other signal along the y-axis and look at their intersection, for example, this is the oscilloscope screen and this is the vertical axis and this is the y-axis. So if we let V sub 1 oscillate along the x-axis and let V sub 2 oscillate along the y-axis, if this is signal 1 and this is signal 2, At a certain time lapse, for example t sub 1, they have an intersection at this point. So also, at another time lapse t sub 2, they have an intersection at this point. So if we try to plot the points of intersection when they oscillate simultaneously, we will be able to observe a pattern. It's hard to demonstrate without using an actual oscilloscope, but I'm going to show you a simulation. So for example, the frequency A is equal to 1 Hertz and the frequency B is equal to 1 Hertz. So in other words, the two signals V sub 1 and V sub 2 have equal frequencies, and notice that their intersection with respect to time, when you let the oscilloscope run, will look like a diagonal line. But once we vary the phi or the phase angle, this one, let's try to vary the phase angle. So it looks like a rotating circle with respect to the vertical axis. It's a slanted circle. However, if I try to double the frequency of one signal, for example, the frequency of the second signal, the pattern looks like this. What if I try to double the frequency of signal 1 with respect to signal 2? Notice that the pattern is now symmetric with respect to the horizontal axis, and it's rotating as if its axis is along the horizontal. And if I try to assume that signal 2 has a frequency of 4 Hz while signal 1 has a frequency of 1 Hz, meaning to say that there's a ratio of 4:1, let's see what will happen. Notice that the pattern changes as if there is a presence of 4 continuous parabolas rotating along the vertical axis. So this is what we call Lissajous figure or Lissajous curve, and it has many applications, but I'm going to focus on the most practical one. For example, if I have a circuit or an electronic component like a crystal, usually crystals are present in microcontroller because it can help the microcontroller to calculate for the exact time intervals of different processes or calculations that the microcontroller performs. So for example, I have a component, it has an output, and I try to feed this output into an oscilloscope. So remember that there's a port here. If I know in advance that this component has a frequency of, let's say, 100 Hertz, and when I try to use this in my circuit, or when I try to design a circuit and use such component, I notice that there's something wrong with the calculation, and I want to know if my component is possibly broken. It's not giving me the exact 100 Hertz of signal oscillations. To explain this in greater detail, let me use Tinkercad. So this is an oscilloscope. Using these components, I can build a circuit that yields a sinusoidal waveform, and I'll feed that output into my oscilloscope and observe the waveform. But if it's your first time to use oscilloscope, you could actually feed a known signal to this oscilloscope using this, what we call, function generator. When it's your first time to learn oscilloscope, function generator comes hand in hand, or it helps you learn oscilloscope because you're able to produce waveforms with specific frequency, amplitude, DC offset, and so on. So let's assume that signal 1 comes from this function generator. So I'll connect this function generator to our oscilloscope. I'll just click this terminal, and Tinkercad will automatically create a wire. I'll just recolor this wire with red, and then connect the negative terminal of the function generator to the negative terminal of the oscilloscope. I'll recolor this to black, and if I try to run by clicking this start simulation, notice that the oscilloscope is displaying this graph or plot of the voltage versus time plot. So I'll stop the simulation and try to adjust the settings. So once you click this function generator, it will show you the different settings. So I'll just click, for example, 100 Hertz, and then the DC offset to 0, then display a sine function, and let's see, let's start the simulation. So notice that the frequency is too high because I'll stop the simulation, and once I click this oscilloscope, notice that the time per division is 100 milliseconds. So let me try to decrease the frequency to let's say 10 hertz. When I click the oscilloscope, there's no option to change the voltage per division because apparently this is a simulation. So the oscilloscope can actually automatically update or adjust the voltage per division of the screen. So going back to the oscilloscope, if I try 10 hertz, let's see. So I'll stop again and let me just change this to 1 millisecond for the time per division. How about 10 milliseconds? Okay, it's beginning to take shape. Okay, I'll just stick with 100 milli. So I'll stop there and I'll copy the same setup. So this time, going back to our figure, remember that we have this imaginary component that we would like to test because according to its data sheet or according to the label coming from the manufacturer, it has a frequency of 100 hertz. This component, this can be a circuit or a crystal oscillator, whatever. It has a frequency of 100 hertz, but when I apply it to my circuit, it doesn't function properly. So I suspect that maybe my component is broken, maybe it's not operating at a frequency of 100 hertz, maybe lower than that or higher than that, and so on. So I'll assume that such component is represented by this second function generator. So let's assume that this one has a frequency of 100 hertz. And this one also has a frequency of 100 hertz. So if I try to run the simulation, so let me update its time per division to 1 millisecond per division and then run the simulation. So I'll have this figure. They have similar waveform because they have equal amplitude and frequency. So I intentionally did that. But what if in reality, since I assume that my function generator is actually my unknown component, my component that I suspect that is broken, and it actually has a frequency of 101 hertz. By inspection alone, that 1 hertz difference is not visible in my oscilloscope. They still look similar, but there's actually a huge difference. And in some applications, this difference of 1 hertz is crucial in some circuits. So apparently, by visual inspection, this is hard to detect, this difference. And this is where Lissajous curves comes in. Even if you have a single difference of 1 hertz, for example, signal 1 has a frequency of 100 hertz, and this one has a frequency of, so the limit is 20. So I'll just assume that this is 19 hertz and I'll try to play it. Notice that the pattern actually amplifies that difference, but when they both have equal frequency, 20 to 20, let's try to animate it. It looks like a perfect circle and it rotates this way. Unfortunately, I cannot oscillate one signal along the vertical axis because this is just a simulation, but in many oscilloscopes, you could actually transfer the oscillation of one signal to the vertical axis and not just along the horizontal axis, and you will be able to observe Lissajous curve. And Lissajous curve actually tells you that if two signals are equal, meaning to say they have equal amplitude and frequency, regardless of the phase difference between them, they must be displaying a slanted circle that rotates along the vertical axis. Otherwise, if there's some small differences between the frequencies of one signal, there will be a change in the Lissajous curve or Lissajous pattern. So for example, if this is 11 hertz and this one is 12 hertz, you could actually see the difference. But if they have equal frequencies like this, then you will be able to observe a circle. So apparently in oscilloscope, when you try to observe two signals and you want to confirm whether the other component using a function generator, recall that the lower function generator here represents my electrical component or electric circuit with a fixed frequency, and I try to compare it with a function generator, and at this point it already looks similar, so I could deduce that using my function generator it has a frequency of 100 hertz. But if you try to transfer one of the oscillations into the vertical axis, because apparently right now they are traveling along the horizontal axis. They exhibit the same waveform, but if I try to plot their intersection, I'll be able to display the Lissajous curve, and most oscilloscopes actually allow that kind of setup wherein you feed it with two signals and then try to superimpose those two signals in such a way they vibrate perpendicularly with each other, and the oscilloscope just displays their intersection. And when you plot them over time or with respect to a varying phi, then you could actually see a dynamic pattern or a revolving pattern around a specific axis. When the two signals are perfectly equal, they have equal frequency and equal amplitude, you will be able to observe a slanted circle rotating along a specific axis. But once they have a difference in the frequency, even for a small amount, so you will be able to observe a totally different pattern. So in summary, Lissajous curves can actually be used to test the actual frequency of an unknown component. We could actually use Lissajous curve to determine the exact frequency of the unknown component. So again, one practical application of Lissajous curve is that when you have a component and you're not sure of its frequency, then you can connect it to an oscilloscope and a function generator to an oscilloscope and observe their Lissajous figure or Lissajous curve. You keep on adjusting the frequency of the function generator until it produces a figure like this. And once it produces a figure like this, then whatever the current frequency of this function generator, then that would be also the frequency of your unknown component or circuit. So that's one practical use of Lissajous curve. Don't forget to like this video, subscribe to my YouTube channel, and hit the notification bell button for awesome updates. Thank you for watching!